Welcome, everyone. We are going to start the seminar in about 1 or 2 minutes, okay? We're waiting for more participants to come in. Thank you. Okay, welcome, dear participants. We will begin our seminar. And I have a quick reminder that please make sure that your Zoom display name matches your full name as used during registration as first name plus last name. And by joining this session, you're considered to have accepted the data privacy consent as part of your registration process. During the session, you may ask your questions either by unmuting yourself and speaking directly or by using Q&A or chat sections. And thank you for your participation. And we are starting now. It's a great pleasure to open the second session of 5 Beats of Intelligence AI Meets Diverse Domains seminar series. This is a joint initiative under the EuroCC-4C project. As you know, EuroCC-4C brings together the national competence centers of Turkey, Serbia, Montenegro, North Macedonia, and Bosnia and Herzegovina. This seminar series is one of our collaborative activities designed to highlight how artificial intelligence intersects with various scientific and societal domains. Once again, I would like to express my sincere thanks to all country representatives and project partners who have contributed to making this series possible. Today, we are continuing with a talk titled AI Meets Biomarkers of Aging, and our speaker is Dejan Babic, a researcher and lecturer at the University of Donja, Gorica. I hope this is correct pronunciation in Montenegro. Let me briefly introduce him. Dejan holds a master's degree in artificial intelligence and is currently pursuing his PhD in information technology. His main research interest lies in applying artificial intelligence to identify non-invasive biomarkers of aging. He is also involved in projects that combine artificial intelligence with Internet of IoT, HPC, and blockchain technologies in domains such as healthcare, smart systems, and supply chain traceability. We are very much looking forward to his insights today. Dejan, if you're ready, welcome first, and the floor is yours.
Thank you very much, Susan. I will just open my camera and wave to everyone. I'm in one classroom here at university. I have a very bad internet connection, so I will just close my videos to have the most of the internet as possible. Susan, thank you once again for the introduction. I will just try to share my screen fast. Okay, can you just confirm that you see my screen?
Coming now. Could you please turn it to presentation mode?
Let me just a second.
I think
Okay.
it's coming.
Yeah.
Yes, now it's okay.
It is good?
Yes, perfect.
So good day, everyone, and thank you for being here today. Today, I'll be presenting a topic that sits at the intersection of artificial intelligence, medical imaging, and preventive healthcare. And it's about the AI and how AI can be used to identify biomarkers. And I will also present AI Age project, which targets this problem. Before I dive into the science, I will just briefly introduce these very pretty people at these following slides. We are all members of AI HPC department at University of Donja Gorica. Our team is made up of AI researchers, PhD students, HPC specialists, and domain experts. Most of us here at these in this team are also members of our NCC Montenegro too. We are a very young team and we have an interdisciplinary focus in many domains. Here at this link at the bottom of the slide, you can check us and our research at the research gate. So I will briefly explain or just provide an overview of key topics I will talk about today. I will introduce you to the AI Age project. I will provide just some broader context and motivation for biomarker research. I will also talk about some milestones in this project. I will also briefly, I'm not an expert, but I will try to explain some foundational concepts like what the biomarkers are, why the retina is uniquely valuable, and why do we do all of this. I will also present two of our research efforts, our current core contributions within this project, the retinal image quality assessment and vessel segmentation using deep learning. And at the end, we'll just have some little comment about what are the future directions and what future research in this project will target. So what exactly is the AI Age project? It stands for Artificial Intelligence Supported Identification of Novel Non-Invasive Biomarkers of Aging. This project is a collaborative initiative between Faculty for Information Systems and Technologies at University of Donja Gorica and Faculty of Medicine at University of Montenegro. It's a nationally funded project. It's funded by Ministry of Education, Science and Innovation. There are a lot of project aims, but I will talk about the primary objective or the aim. This project primarily investigates the use of AI to extract biomarkers from retinal images, enabling better monitoring of aging and disease progression. The goal is to identify non-invasive digital biomarkers and patterns that can be actually captured using imaging and then interpreted by machine learning models. The eye and specifically the retina is a powerful window into vascular and neural health. Also, what I'd like to mention is that this project tries to utilize a large dataset of retinal fundus images from the UK Biobank to develop predictive models. Let me share a few highlights of what we have achieved so far. We have AIH and provided us with new computing node. Through this project, we successfully enhanced the HPC infrastructure at UDG. We also began patient recruitment in primary healthcare clinics in Podgorica, building a local or a national dataset of health data. We have also successfully gained or secured access to the UK Biobank, which includes over 130,000 retinal fundus images, and we like to call it a gold mine for AI research. And currently what we're doing is we are finalizing two research articles, one on our custom segmentation method for blood vessels from the retina, and another one is about retinal image quality assessment on whose I will talk about, on which I will talk about a bit more in depth later. So I will just pause here and introduce you to a couple of very important concepts, so you can follow me a bit later. So what is the retina? Retina is a neural tissue layer in the eye that captures light and sends visual signals to the brain. It contains a dense network of blood vessels, making it an accessible, non-invasive source of vascular and neural biomarkers. It being non-invasive is very important as it can be photographed by specialized cameras. On the photo on the left is a representation of 3D representation of the eye, and the retina sits in the innermost layer of the human eye. But when you photograph it with the specialized camera, you receive a 2D appearance of retina. And I would just like to emphasize on how important it is for this to be non-invasive, which means that you don't need any, you just take a photo of it and the patients don't have any problems after. Also, what are biomarkers? What is a biomarker? Biomarker is a measurable indicator of a biological state. It can be a molecule, it can be a gene, protein, or even a visible pattern in medical imaging. So what we are trying to achieve, we are trying to achieve to sort of predict the biological age of the individual from the analyzing the retina image. It's one of the most exciting areas of research today. Biological age of the individual in a lot of cases can differ from the chronological age, and therefore that can indicate and say a lot about the person's overall health. So we basically want to use human retina image to predict the biological age of the individual, as I stated before. So this is not a straightforward process. Why? Because I will talk about those challenges a bit later, but let me first introduce you to the ladies on the right of the slide. They are the part of AI Age project team, and they are an invaluable resource for this specific project aim. Both of them are medical doctors and experts when it comes to analyzing human retina. Their inputs and research on biological age and annotations, which we'll hopefully use to train AI models, will be of an invaluable resource to us. So what are the challenges here? First, it's the datasets we use vary in image quality in the sense of them being adequate for specialized or medical analysis. Also, subtle changes in vascular structure in retina are not always visible to the naked eye. And most importantly, the chronological age is easy to obtain, as we know, right? But the ground truth for biological age is much harder to define. So we are sort of leaning here on Natasha and Isidora to figure those annotations for us out so we can make the best model as possible. So we tackled the easier problems first. We developed AI-based retinal image quality assessment tool or model. And also we have developed an AI-based vessel segmentation model also. And I will talk about these right now. So the dataset that we're planning to use from the UK Biobank contains over 130,000 retinal images. By going through some research that targets the medical quality of these images, we found that over 25% of those images lack medical quality. They are not suitable for medical analysis. So if you want to use as many images as possible for training your AI model, first you need to verify that the images are of good medical quality, but you also want to use a lot of those images. But if you try to do it manually, it's almost impossible. So the manual image creation is just not feasible. So we first started with the question how we can automate this process, and then we figured that we can develop a model that can detect the quality or classify the quality of the image, and therefore we can sort of automate the selection of the images that we will further use for some other analysis. So initially for this problem, we used 2074 images from the original UK biobank retinal dataset. These were manually annotated by Natasha and Isidora. And I will just briefly talk about how they did the annotations. They focused on clear visibility of the optic disc, of macula, fovea, and capillary plexuses. You can, on the right, you can see the differences between two images. The image on the left expresses these a lot better than one on the right. The left one is more suitable for medical analysis than the one on the right. So what the methods we used, I would just like to point out that I will try to be brief as possible in explaining these methods and the results. So I'm creating some room maybe for some questions later. So we approached with the transfer learning method. We used Swin transformer and ResNet enhanced with attention mechanisms for feature extraction. We used Swin and ResNet because they are known to work the best with images of high resolution. What is interesting to point out is that no explicit preprocessing was applied to the input images. We tried to keep the original images in the original dataset as original as possible to sort of simulate that real conditions. And the only augmentation techniques we employed are only the horizontal flipping. We sort of made the mirror images of these, like this one, for example. We just made the mirror images of those, and we before the training of the models, we had a data set of 4,148 images. After the training of these models, Swim Transformer performed very good. It had an accuracy of almost 95%. It had accuracy of like 94.96, I think. And its F1 score was very good. For this task, ResNet plus attention model worked a bit worse, but it was still also good. 94.22% is its accuracy on this task, and F1 score for it was 93.6%. So I will go to the next research we did. It's about retinal vessel segmentation. So first, I would like to answer the question of why do we care about segmenting retinal blood vessels. It's because their structure reflects cardiovascular and neurovascular health. So again, I'm not an expert on this, so take my words with a grain of salt. I hope that I see that Natasha and Isidora, I see that Natasha is here. So maybe if you had some questions about the medicine aspect of this stuff, you can ask. Maybe she can answer instead of me. So I'm just trying to briefly explain these problems and why do we care about them. So the structure of cardiovascular and the neurovascular health is presented in the vascular maps of retina. The experts can analyze the original image, but it's better if that image is transformed into the blood vessel map. And segmenting these vessels can provide deeper insights into some systemic conditions. For this problem, we worked with the STAIR database, unfortunately, because at the time we worked on this, we didn't have an access to UK Biobank. And as far as I know, the UK Biobank doesn't have many annotated or many segmented maps of blood vessels. Why? Because this is a really slow process. Every image needs to be annotated or drawn by hand. As you can see from this STAIR database, which has 400 images, Natasha segmented 37, Hoover and Kuznetsova segmented 20 images each, and we couldn't find any other annotations of these images. So we're pretty low on the real segmentation maps. So we used some augmentation steps for this to sort of make a dataset bigger. Unfortunately, this is a small data set to be used for training of AI models, some AI models with bigger input shapes. So we thought about how can we make a bigger data set and then make a smaller input shape into the model. So we got an idea to create our own data set out of these original and annotated images. So what we did, we extracted 29 by 29 blocks from both original and annotated images, and then we tried to make our own classes out of this. I will try to briefly explain how did this work. We labeled these batches as vessel or non-vessel based on the center pixel. If the center pixel of the original image had an blood or annotation in the middle of this segmented block, then we said, okay, this is the block that is labeled as vessel. And on the other side, if we didn't have that in the middle of that block, we have labeled it as a non-vessel block. So effectively, we made bigger data sets out of these original images. And I also forgot to mention that we made a couple of models. We tried to make a couple of models. For example, let's say we tried to make Natasha's model with only her annotations, Hoover's model with only his annotations, and Kuznetsova's model with only her annotations. And at the end, we made a combined model. We tried to combine every image we had in the annotated database. So that's why we had two datasets actually, two sizes of the datasets. We had one that had 1.31 million blocks, and the second one that had 736,000 blocks for one training dataset. So this is the architecture of our model. It was trained over every experiment we had. Our model was tried different architectures. This one proved to be the best in terms of metrics and terms of the actual look of the annotations. We trained the models in 100 epochs. The training of the model, depending on the model, was from 25 to 50 hours per model on an HPC. And this architecture, or this CNN actually, had somewhere close to 500,000 parameters. This architecture was also adaptable, which means that it can segment the images of different sizes, actually. How is that segmentation, the process of segmentation done? We implemented a sliding window approach or sliding window inference. How did it work? It worked by feeding each 29 by 29 patch of the original image into a model and reconstructing the segmentation map pixel by pixel. Although this was computationally intensive, but it allowed us for precise and fine-grained vessel maps. Plus, it was highly suitable for paralyzation. So this is how the parallelization looked like. Initially, the segmentation process took up to 35 minutes per image, I think. Yes, it was 35 minutes, which was for us clearly unsustainable. So what is the idea of this? If you have 30,000, let's say 30,000 original images, how can you as low as time possible, how can you, with the model, segment all those images? So that's why we also implemented this polarization approach. And you can see that for one CPU, it took for 35 minutes to segment the whole image. When we parallelized it on 2 CPUs, it took 18 minutes to segment the image. And on 4 CPUs, it took 10 minutes. The efficacy of this approach started lowering down, so we stopped at four CPUs to make the most of all the CPUs we had on that cluster. We tried the parallelization on. So these are some metrics of the models we developed. By metrics, the Adam Hoover model had the biggest accuracy in every metric, but we discussed that the combined model, being that it's seen all of the annotations, was more robust in real sense. So I just saw that I didn't provide an image of actual segmentations of our model. So I will stop here. I know that I don't have anything after this. So I will just, Professor Tomo told me that he would give a comment at the end of my presentation. I don't know if he is here right now. Maybe he or Natasha can comment on our future, maybe research directions regarding this project, while I try to find the image providing real segmentations of the models we developed.
Tomo, welcome.
Hey, thank you, Sezen. It's good to see you.
Good to see you too.
Thank you really for organizing this event. It's always a challenge to gather people from different countries, from different teams. For us, it was last week was also challenging because we had holidays for 3 days out of 5 days. But I hope that we will have successful series. Dejan, thank you for the presentation. We kind of try to make it brief as possible. This is the effort that's tied to a national scientific research inspired and instigated by the group of researchers from the Faculty of Medicine here at Podgorica, Montenegro. Of course, our group here is trying to utilize different tools and different algorithms for a few of these very specific applications that need to be done. In the first step, one of the kind of general topic that we are addressing is this segmentation of blood vessels, and that's been done, through several iterations. One of them is detecting or identifying or separating good pictures from bad pictures, because when you are taking these pictures, it takes you a few shots to get the right pictures. And then, of course, there is this major challenge that's still ahead of us in next 2 years is how do there will be other prediction models developed, but how do you really, in several steps, come from the image of retina, which can be obtained as a non-invasive, a process that for the patient can assess, get some information about the condition of the patient and then assess their age. Isidora, Natasha, do you maybe have any comments here or?
I would like to thank Dejan for a very inspirational presentation. These are only first steps. For now, we maybe figured out how to do the quality assessment. That's just the beginning. The next step is detecting pathology through vessel segmentation, like Dan presented. But our ultimate goal is to actually to be able to detect other anatomical or pathological features in retinal images, and that will be possible through methods that will analyze the whole image. So not just the tracings of blood vessels, but we will analyze the image as a whole. And we have already started working on that. That will be it for now. I think that United Kingdom Biobank is really opening a lot of opportunities because there is a great number of images that are well annotated regarding the characteristics of patients, like their age, socioeconomic status, and also medical problems that they have. So the data that we find in the retinal images can be correlated to all of those characteristics. And I think we are just at the beginning of very interesting research.
And maybe very important thing to mention is that as time goes, more and more powerful AI models are available, or tools available to us. So there is less limitation on the models and much more limitation on the quality of data and the actual data set that is really representing the problem that you're trying to solve in the right way. So if you have a good data set, there is almost no question anymore if you can get the prediction model based on the data set to repeat what it's supposed to do. And this is actually where HPC is really playing a major role, because most of these new models are getting bigger and bigger, more complicated, and they are requiring much more resources with respect to the CPU power or GPU power, and also the memory that's required to train these models or fine-tune them, or even later on when you train them to utilize them. So this is what is happening, and it is happening really dramatically. I mean, maybe it's been happening before too, but before our eyes we can see, if you get some results, you need to present them, utilize them, publish them. Otherwise, 6 months from now, you're already obsolete. So it's really interesting.
Tomo and Dejan, I have one question. When you talk about the HPC systems, are you using any supercomputer or your own workstations for your research, or just in the planning phase, this thoughts, and you're going to continue?
Yes, this is a good question. So what happened with this project, there was another project before that we implemented in between, EuroCC-1 and EuroCC-2. There was for us this pause due to the Digital Europe. It's similar as you had this challenge. During that time, we had another project that allowed us to purchase 2 computing nodes for local use here. They have a few of these GPU cards, and you can log in, use the Slurm, and run some jobs. And to be honest with you, it took us a year to really figure it out how we are going to use it the best way. And the main goal was not that much the computing power that you get, but the hands-on experience. How do you install this? How do you manage it? Our colleague Luka Filipovic was helping there a lot. And then with this project, we purchased another computing node, which is a little bit more powerful with respect to the GPU card and CPU node. So all of these experiments are run on either Google Colab initially on the cloud, or on these computing nodes that we have. And we are now also in a consideration and a process of applying for either benchmark or development call for EuroHPC, and we expect that to happen between now and September, maybe, to put up this application, just to time it. If it's a development, we can do it right now, because but benchmark, you really want to be ready to know what exactly you want to run, and then to run it. So that's the plan for the next month or so.
That's good news. Any other questions or comments from participants or Dejan? I guess no questions on chat, no questions on Q&A board. Tomo, do you have anything to add?
Not at this time. I'm really happy.
Okay.
I'm sorry I missed the meeting in Belgrade, last week, but I was weighing. I don't know if anybody from Turkey was there or
No.
It was a good meeting from what I hear from Bojana and Enis,
Yeah.
but so really good. Okay.
Yeah.
Okay,
Dusan
very
and
I found the
Dejan.
sorry sorry for interrupting. If you
No.
have something to say,
No, please.
I found the images I forgot to put on the slides for the real example of the.
Do you want to show it?
Yeah, of course.
Yeah, for sure.
Let me just quickly share. So this is actually how the model segmented the real images.
Mm-hmm.
And how it looked in the end. It was a bit overfitted. It picked up some background pixels, but with removing that noise, we're left with the image that's far to the right. So this is how those annotations look like. And this is really good for automating a lot of images. Then you will have a lot of images that you can analyze just by their blood vessels. Also, I would like to pinpoint something. All the images you saw of retina or on these slides, my slides, they're not taken from internet, not taken from some databases. This is just what the ChatGPT or the base models that create images created for me while I was preparing this presentation. Now just take a look at this photo, this synthetic data that looks like exactly like the original images, and this it can strike a lot of questions about what can be done with the generative AI regarding these problems also, considering retina and another research projects.
Thank you, Dejan, for the addition.
Yeah, I think this is a really good example. There was a similar research implemented here. My colleague, he is 16 next year to me, Stevan. He was doing like detection and segmentation of chickens in the chicken farm, and in the second round of his experiments and research, these tools for synthetic data generation were so powerful that he was able to utilize a much smaller data set to drive the synthetic generation tool, and then to generate prediction models based on synthetic data and get fairly similar results on the prediction model as it was done with the actual data. So this is kind of some possibilities for research, at least that are ahead of us, or probably are already happening, but we just have to pick up the pace, and catch up with the flow. So this is very interesting there.
Yeah. Thank you. If there are no more questions or comments, I would like to sincerely thank firstly Dejan Babic for his presentation, and Tomo for your insightful comments and additional information contribution. Thank you. Firstly Dejan, then Tomo and Natasha for her comments. Do you have anything to add, Dejan? No? Okay, thank you. Thank you. And our next seminar will take place in the second Tuesday of June, June 10th. And don't forget to register for the third seminar. We look forward to seeing you in the next session. Thank you all for joining, and have a great day. Thank you.
Thank you,
Susan.
Thank you. Bye.
Bye.
Bye.